Hey folks, for the last part of our chapter 24, we're going to talk about Gauss's law and how it involves conductors. So all the other examples we've done were with insulators, where we had charge stuck within the insulator. That we maybe have a ball of plastic or something like that, where you could theoretically put charge inside of it. Well, for conductors, we got a different situation. Okay, conductors allow the free flow of charge. And a quick reminder, let's say you have an electric field. Okay, so let's say there's an electric field there and you have an electron in that field. Well, that electron is going to feel a force in the opposite direction of the field. Now, by the way, if you could have a positive charge in that field, it would feel the force in the same direction as the field. So charges will move if there's an electric field and if the charges are indeed free to move. Now, in our previous examples, in our insulators, the charges were stuck in place, so they weren't free to move. Well, with conductors, charges are free to move. So for instance, let's say I gave you the following situation. Let's say I gave you a metal ball, a solid metal ball, and at some instant moment, I filled it up with negative charge. So inside and out, it's full with negative charge. Well, there would be, these charges would make an electric field pointing inward, and I'll draw that. So it would look something, it would be in this direction. It wouldn't quite look like this, but it would be in that direction. Well, if I'm one of those electrons and I'm free to move, I'm going to move against the electric field, okay? So if you look at the result of that, all those extra negative charges are going to move outward until they're all at the very, very outer edge of the conductor. And then what will the electric field inside that conductor be? Well, it's going to be zero. So conductors allow the free flow of charge until the electric field within the conductor is zero. At that point, the conductor has achieved electrostatic equilibrium. Now, in future chapters, just as a side note, in future chapters, we're going to apply electric fields to conductors, and we're going to keep that electric field there. And then something different happens. But for all these examples, we're going to say the charges will move until the electric field within the conductor is zero. Another example. Let's say that I have an electric field. Something is creating this. It could be charge. It could be something else. But here's an electric field, okay? And then let's say that I dump a piece of metal into that field, okay? Well, charge in that metal is going to flow. Specifically, electrons are going to flow. Now remember, electrons go the opposite way of the field, or they experience a force in the opposite direction of the field. So here's what happens. That's the before picture. Here's the after picture. So we'll draw the same field, okay, like so. There's your electric field, and here's your conductor, okay. What will end up happening is a bunch of electrons will move to the left side. Now, that's going to leave behind a bunch of extra positives on the right side. Those positives and negatives make their own electric field to the left, and that electric field that I'm drawing in green will exactly cancel out the red electric field, meaning the electric field within that metal conductor will be zero when all is said and done, okay? So that's the first rule. The electric field in a conductor that's in electrostatic equilibrium will be zero. It turns out there's several rules about conductors that we're going to use. Okay, so that's rule one. The electric field in the conductor will be zero once electrostatic equilibrium is achieved. As a result, the Q inside the conductor will be zero. You'll notice that in both these examples we drew, there's charge on the very outside of the conductor, but there's no charge on the inside. Same thing with this guy here. The left side becomes negative, the right becomes positive, but everywhere within the conductor, the charge is zero. Okay, so that's rule number one. Rule number two, if there is any net charge, we'll call that Q, it's going to reside, or it resides, only on surface. So if you look back at our two examples here, yeah, we end up with charge on the surface there, and we end up with charge on the left and right surface there, but nowhere else, okay? For number 3, this is a little confusing, okay? The electric field near a surface is equal to sigma over epsilon naught. Now, you might recall, and that this sigma is the surface sigma, okay, the surface sigma. So let me explain. So let's say you have this conductor right here. So let's redraw that, and it's in that field. So you've got negative charges here, and you've got positive charges there. Okay. If we call this sigma, all right, that's the surface charge density. And then if we do Gauss's law, so imagine I have, this is a cylinder, but I'm just looking at it edgewise. Well, on this side, we have an electric field pointing toward those negatives, okay? But there's no electric field in here, okay? So if we use Gauss's law, you know, double integral E dot dA equals Q in over epsilon naught. Well, this becomes E times, well, there's only this area that the electric field's passing through. So you get A. Q in is equal to sigma times A over epsilon naught. Your area drops out and you get your electric field. But notice that that sigma, it's not like the total sigma for the shape. It's just a sigma on that particular surface. So for instance, let's say I had a conductor like so, and let's say I add a whole bunch of positive charges to it. So you're going to go like this, okay, and like this. Now, by the way, we're not really adding positives. We'll say we're taking negatives away, leaving behind positives. Okay, so the sigma we're talking about is this sigma, the sigma on only one side. That's different than the overall charge per unit area on the whole thing, because you have a left side and you have a right side. Okay, so it's a little confusing, but in this equation, sigma just means a sigma on one surface. Okay, and then the final rule for number 4 here is that surface charge density sigma is greatest for small r. So let me kind of explain that one. Let's say you have an irregularly shaped object, okay? You're going to get more charge at the corners, okay, like so, than you're going to get at the smoother parts. So and again, partly because the charge is trying to get away from each other. They're repelling each other. So that's as far away as they can get. And again, they're going to arrange themselves such that the electric field in the conductor everywhere is 0. Okay. Now, in the next video, next 2 videos, we're going to do some examples with different shapes for conductors and different charge distributions on the surfaces of conductors. But if you remember these rules and what happens, figuring out the answers to any kind of question that you might be asked about charges on conductors is actually relatively easy. So I hope that video was helpful, and thank you very much.